Hey YouTube, welcome back. Today we have our sixth video or seventh video. I lost count of our series Design a Key Value Store. Today we talk about uh, versioning, the consistency resolution, which is versioning, and if you didn't watch the previous videos, I highly recommend to watch them so you understand what we are doing. However, if you watch the previous video and you just need a quick recap, I will just make it in a bit right now. So we have a series that we are talking about design a key value store, and we said all the time that it's in system design interviews all the time the question are pretty vague. So our job as an interviewee is to get ask as much as we can clarification questions so we can understand the problems and understand what exactly our interviewer wants us to design. And after that we propose high level design, and after that we get deep dive in specific components that our interviewer want us to get deep dive in it. And after that we wrap everything up. Maybe if we have time we could talk about performance increasing and stuff like that. So we have this framework that we use for every single system design interview, that we understand the problem. And as I'm saying all the time, this is the most important step, understanding the problem. We After that we propose a high level design, and after that we get deep dive in some aspects of the component, and after that we wrap everything up. And into the questions, the understanding the problem, we ask maybe from 5 to 7 questions. I will not go with all of them because we have a video talk about them already. And with the questions, well, after asking the questions, we have an idea of our functional requirements and our non-functional requirements. And it's really important that even though if we think that our functional requirements and non-functional requirements are the best, or like we really understand the problem, it's really important to ask our interviewer, is there anything that we are missing or something like that, to make sure that we really exactly design the things that our interviewer wants us to design. Because it's communication is a big part in systems and interviews. Communication, and all the time we ask for clarifications. And after that we talked about the CAP theorem, the consistency and availability and the partition tolerance. And we talk about the difference between we said that it's impossible for any distributed system to guarantee the three things right here: the availability and partition tolerance and consistency. It's maybe we could take AB, like take availability and partition tolerance and sacrifice the consistency, or AC, availability and consistency or sacrifice the partition tolerance. And with the AC system is not real world system, because a partition tolerance is not something that we can avoid. So all the time we choose between AB and AC and CP. And we said that because our requirements is that we require high availability, so we're talking about the EV. Our database should be highly available. And after that we talked about the data partitioning and how we can store the key on a ring, because one server is not enough to store all of our keys. So we store a key in nodes. And we the way that we could store the key in nodes, we can use like um, a hash ring, and we go clockwise and we store it in a specific server. And after that, because we want a maximum availability, we'll store the key in multiple services, so we create replicas. And we also could store our data into multiple different availability zones and data centers, to make sure that we have no loss in data. And because we have high availability right now, we have the consistency problem. And we said that how to handle the consistency problem. We talked about one of the aspects that could solve the consistency problem. We talked about the quorum consensus, and how quorum consensus could help us to guarantee that we have some level of consistency. and basically we have a coordinator that acts as a proxy and makes sure that the coordinator waits for response from the servers or from the nodes. And maybe for example, if the w or like the write quorum size is 3, so when a client to try to make a write operation to the coordinator, the coordinator waits at least for 3 requests from requested from 3 servers to tell the coordinator, yes, we are yes, this you can assume this operation is successful. And if for the read quorum size is 2, so the coordinator only waits for 2. And we talk about this is a trade-off between consistency and latency, because the more you put in the write, for example, that means it will take more time, and that means we have low latency. And the less you put, that means to be you will have high latency, sorry. And the less you put, you will have pretty low latency, but consistency is not guaranteed. And we talked about after that about the consistency model, and we talk about strong consistency and weak consistency and eventual consistency. And we choose the eventual consistency because it's suitable for our application right now, and this is what Cassandra and DynamoDB using. So it's a technique that it's widely used. And we talk about the conflicts that we could have. For example, if we have server 1 and server 2, and server 1 updated d1 and have d1 just like database 1 has name equal Jon Snow, and server 2 oh sorry, let's just put the name here, John. Okay, so let's assume that server 1 and server 2 has d called John, and has name called John, and server 1 change John to make it Jon Snow, and server 2 change John to make it Ali, and both of them change it simultaneously. So basically we have right now conflicts. So these conflicts, how we can solve them, and this is what we're going to talk about. In right now we have inconsistency and we have conflicts and inconsistency resolutions. And to solve this one, we can use versioning. Versioning is related concept in the context of management and distributed systems and database. Um, the, the versioning plays a crucial role in handling conflicts and maintaining the integrity when multiple replicas or nodes in distributed system attempt to modify the same piece of data uh, concurrently. So how this work? We have, maybe we say that there is 3 or 4 steps. First of all, we use versioning. Versioning involves assigning a unique identifier or timestamp to each update or modifications made to a piece of data. Conflicts detection. With versioning, it becomes possible to detect conflicts when multiple replicas attempt to modify the same data concurrently. Conflicts occur when the 2 or more data replicas have different versions of the same data and need to be resolved. The conflict resolutions, when conflicts are detected, a conflict resolution mechanism comes into play to determine how to reconcile state. The conflict resolution process can involve comparing versions, apply predefined rules or policies. So the thing that right now we know how they are working. We could use something called a vector clock, and a vector clock, it's just let me give you an example here. A vector clock, it's use a server version. You can think of them like a key value. It's not a key value, it's like a server, and we have version. How I can put the array oh, okay. So it's a vector is like a server version pair associated with data item. It can be used to check if one version precedes, succeeded, or conflict with others. Let's assume that a vector clock is represented by, for example, let's just talk about how it's represented. So let's say we have D, and we have let's say that we have D, and we have, let's say that maybe like S1, P1, let's say that we have S2, V2, and let's say that we're going until the point Sn, Vn. Okay, so let's assume that the vector clockwise is presented like that. Okay, and where D is the data item, V1 is the version counted, and S1 is the server number, maybe like IP address, something like that, server ID. If data item D is written to server SI, the system must perform one of the following tasks. We will increment VI if CI and VI exists. Otherwise, we create a new entry. Let's see how that works. Let's just start. So let's say that we have we have a piece of data, and let's say that no, I don't need this one. Yep. No. And okay. And just text, and I will say that, let's say that we are right. How can I make it yeah, right, handled, let's say right by xy, right by x, sx, okay, sx. So let's say that sx is making a right right operation to the database. So our versioning, or our vector clockwise, will work like that. We will have d1, and it will equals sx 1, and let's just, so we talk about that d1 will equals xx. Let's just make this with different color. Okay, and let's say that right now our server, we have a server called sx, and it make a write operation to d1, and it give it sign it 1. And let's say that sx make another read request. No, sorry. And let's say that, why it's all of them. Okay, and okay. And let's sx make another read request of d1, and let's say that it's changed it to make it 2. So right now we have d2 equals and sx, because it's the same server, it's making the request, so there is no need to there's no conflicts right now. So sx made a write request, and it changed it d1 and make it 1, and after that when sx change it d1 to d2, there is no need for us to store D1 or care about it, because actually D2 is built on top of D1. But let's say that we have two clients, okay? We have two servers, sorry, two new servers, okay? And we have, let's say, sy, and sy will change it to make d3. So d3 will equals so so it will equals sx and 2, and it will equals the old one is y and 1. Let's just say that this is by right, we make a right by sy, and we have another one. Let's just have another one here. Okay, and this is let's say that we have another one by sz, so we have d updated by 4, so we have d4, and when we have d4 it will be let's say maybe like sx will store sx as usual 2, and we have sz, which equals 1. So right now we have this one, this let's just store them like that. Okay, so it's right by let's say it's right by sz, and right now we have two. First of all, let's just talk about what happened here. Sx is right d1, and after that Sx is right d1 to meet d2, so there's no need to store d1 anymore. And we have 2 on top, because it is built on top of it and it's from the same server, so there's no need to read it again to store d1 again. So we have d2 right now, and we have a write by sy, and we have a write by sz, and when sy is writing d2, it will be d3, and it will be sx equals to 2 when here, and sy equals to 1. And let's say that d4 right now, it will have x equals to 2 and xz equals to 1. And let's say that we are going to read these requests from the client. So it will be the client, when the client read requests, it will be, we have d5, which will be have first of all we have s x, for example sx will equals 2, and sy and sy will equals 1, and z will equals 1 also. And let me just okay. Okay, so let's talk about what's happening here. So the client writes data item d1 here, the clients write data item d1, and the write handled by sx which now has the vector clockwise of d1 sx1. And we have another client, okay, reads the latest d1 updated into d2. It's reads the one into d2 and writes it back. d2 descends from d1 because d2 it descends from d1. Uh, we have d2 because it descends from d1. It overwrites d1. Assume that the write is handled by the same server sx, which now has vector clockwise of d2 sx 2. Right now, another client reads the latest d2, okay, updated to d3. Just look at this one and write it back. Assume the write is handled by server sy, it's different server, which now has a vector clockwise of sx2 and sy1. Okay, another client reads the latest d2, this client, okay, and updated to d4 and writes it back. Assume the write is handled by server sz or sz, which now has a vector clockwise of d4 xx2 and sz1. When another client reads d3 and d4, it discovers a conflict which is caused by data item d2 being modified by sy and sz in the same time. The conflict is resolved by the client and updated data and is sent it to the server. Assume that the write is handled by sx, which now has d5, which right now have d5 has a clockwise of sx 3 sy1 and sz1. sx2, sorry, not sx is 3. Using vector clockwise, it is easy to tell that a version x is an ancestor, okay, we have no conflicts right now, of version or y. So sx of is ancestor of version y. If the version counters for each participate in the vector clock of y is greater than or equal to the one in version x, for example here, sorry, the vector clock for s0 1 and s1 1 is an ancestor of s0 1 and s1 2. Therefore, there is no conflicts record. So here there is no conflicts record. Similarly, you can tell that a version x is sibling, or we have a conflict of y, okay, if there is any participant in y's vectors clockwise who has a counter that is less than in its corresponding counter in x. For example, the following two vector clocks indicates there is conflicts here. So for example, let's say that we have a vector clock that s0 equals 1 and s1 equals 2, and s0 equals 1 and s1 equals 2, even though the vector clockwise, can resolve conflicts, there are two notable downsides. So we have all of that, and we can say that there is no conflicts because each, like if you look about the d4 and d3, that each one of them is ancestor of the previous ones, and there is no conflicts at all about that. However, by using the clockwise, it's easy for us to understand what is coming from one specific server, so we don't have any conflicts. Each server has its own unique version of the data, and using and basically we have two problems with vector clockwise. Even though the vector clockwise resolve conflicts, there are two downsides. First of all, it gives some sort of complication to the system, And the other one, the pairs of the server version could grow rapidly. To fix this problem, we maybe like set like maybe we have, because in real world this array to be maybe could be huge, and to solve this one we can just make a limit for specific servers, and and maybe when we exceeded the limit we just remove the old ones. Maybe this problem that we can have some loss in data, but DynamoDB and Cassandra didn't recognize any problem in production about this specific thing. So I guess that it's not a problem that is discovered yet. So this is it for today's video. We talked about vector clockwise and how vector clockwise handling the versioning resolutions, how it's handled the inconsistency, and how we use versioning to handle the inconsistency, and how like for X how D1 when the client update the data and the other clients update the same data at the same time, how we can handle all of that, and how we do all of the versions. And right now we have no conflicts. X equals 2, y equals 1, and SD equals 1, and we know what is what. Maybe we could do other function to just concur everything and make them consistency, but right now we are addressing all of the conflicts. And yeah, that's it for this video. Hope my description was quite good, and that's it for today's video. And if you like my description, make sure to subscribe, hit the notification bell so you will never miss a video, and see you in future problem.